Let us start this lecture with a thought process. Life is like a flame which burns itself from the birth till death. So, in the last lecture we basically derived an expression for burning velocity of one dimensional premixed flame, of course laminar burning velocity. And today what we will do, we will basically take an example how to determine the burning velocity in actual situations, right, that we will consider. Determine the laminar burning velocity SL of stoichiometric CH4 air mixture considering single step kinetics for which average reaction rate is given as kilomole meter cube second, right, is equal to kg 0.3 and C oxidizer 2.5, where 1.04 into 10 power to 11 right. Basically we will have to find out SL. So, by what you call invoking expression for SL using equation, what would be equation that is? Is it, oh, I have not given an equation, this will be 18, equation 18 can half 2 by 9 alpha by rho u nu plus 1 average So, this is a single step reactions, right. So, we are using a single step chemistry. So, I can write down that is methane is reacting with basically 2 of oxidizer 3.76 N2 going to 2 plus 2 water plus 7.5 to N2, right. This is for basically for single step reaction. And we need to evaluate basically all these properties like nu we can find out what it would be, right. We will have to also find out basically the mass fractions of that, right, because we will have to evaluate this m dot triple dash f. So, we know that m dot triple dash f average is equal to nothing but MWF NF, right. So, that is MWF into kg, kg is basically 1.04 10 power to 11, and I can write down xp 15,000 by T into CH. So, if you look at, I can express that C a concentration in terms of the mass fractions, right. That will be or let me write down right now CH4 0.3 into Cox 2.5. But we know the concentration basically Cf, I can write down Nf by volume is nothing but your Nf by volume molecular weight of fuel divided molecular weight of fuel, right, and this is nothing but your, right. So, nothing but your mass of fuel, and V is if you look at this is YV, right, into MWF, and this I can write down MF by M into rho by MWF is equal, this is nothing but here YF. So, YF rho by MWF, right. So, similarly I can write down as Y oxidizer rho by MW oxidizer. So, if I say this is equation 1 and this is 2, then I can put these values of concentration in equation 2 and I can get. Keep in mind that this reaction is basically occurring at where it will be something like the ignition temperature, you can say, right, or I can, if you look at this, if I say my x is 0 and this corresponds to T ignition, this is my reaction rate. So, kind of thing. So, naturally what will happening, this here my temperature will be T ignition. So, T ignition we have already know, I am saying this as a basically some average temperature of between the reaction zone, in the reaction zone where is equal to 0.75, which is nothing but T ignition, right, T adiabatic plus 0.25 TU. So, T adiabatic is not given, but if you look at T adiabatic for this thing will be around 2200 Kelvin, right, 0.75 into 2000 Kelvin plus, and in this example of course the TU is not given, but in real situation will be given. You can say take T adiabatic is 2200 Kelvin and TU is equal to 300 Kelvin. So, 0.25 into 300, so it will be coming something 1724.5 Kelvin. Oh, I am sorry. So, this is coming basically 298. So, this at this temperature, this is corresponding to basically T ignition, right. At that you will be evaluating, otherwise the temperature is changing, where to evaluate, that is the question. So, therefore, this is correspond that, and you will be evaluating that portion. Some average temperature you will be taking, and this average temperature is right. And also the properties you will be evaluating there, right, evaluating at this. For example, like if I want to find out the properties, the Kg of T average will be 114 minus 3, right, and Cp you will be taking as basically 1,271.5. This will be kilojoule per kg Kelvin. And but however, the rho u you will have to evaluate at the again the rho average you will be rho u, in this case properties you will be finding out as rho e is equal to 1.18 kg per meter cube, and this is evaluated at T is equal to 298 Kelvin, right. So, these properties of course will be given in your example, but here you will have to take at that average temperature. But keep now what we will do, we will basically now evaluate the m dot f, and for that we need to evaluate the mass fraction of the methane and the oxidizer. And what we will be doing, we will be taking, because if you look at the mass fraction of the fuel, let us say this is your mass fraction, it will be, this is your Y oxidizer and this is my fuel kind of things, right. This is YF, right, and this will be, it will be highest here and lowest in the product side, right. This is your x is equal to infinity, x is equal to minus infinity, right. And then where you will evaluate, basically you will have to evaluate the average value somewhere here, right, which you will be taking, because each along the x direction is changing. So, you are basically trying to evaluate average property. So, we will be evaluating the properties at average the mass fractions of fuel and oxidizers are to be, mass fraction of fuel are to be evaluated as, let us first evaluate the mass fraction of fuel and oxidizer from basically this expression in the chemical reaction, that is YCH4 will be 16 divided by 16 plus 2 into 32 plus 3.76 into 28, that will be coming around 0.055, and this mass fraction at the inlet or x is equal to minus infinity. Similarly, what will be oxidizer will be 2 into 32 divided by 16 plus 2 into 32, 3.76 into 28, it will be something 0.22. Rest of the of course will be nitrogen, right. But however, when we will use this thing in expression for the mass consumption rate of the fuel, right, per unit volume in equation 2, then I will have to use the average values, right. So, the average fraction of fuel and oxidizer are evaluated as YCH4 is equal to 0.55 plus 0 at the product side, right. At the x is equal to infinity, this will be 0 divided by 2. So, that will get 0.0275 and Y of oxidizer will be 0.22 plus 0 divided by 2, it will get 0.11. So, the equation 2 becomes I can write down as F average is equal to 16 molecular weight into 1.04 10 power to 11 and XP 15,000 divided by what I will be using 1724.5, right. I am substituting these values in the equation 2 and it will be basically rho average, this will be 2.2 YCH4 average by molecular weight of CH4 minus 0.3. Keep in mind that we are substituting CF, right, is equal to CH4 is equal to rho YCH4 average, of course I am taking into molecular of CH4, right. In place of concentration I have taken rho, I have taken out because rho is the average, this thing whichever coming, right. Into similar way I can also put Y average oxidizer MW oxidizer 2.5. And keep in mind that we need to evaluate this rho average, right. Rho average by using ideal gas law, I can find out rho average is equal to P by RU MW mixture into T. So, in this case I will be using the mixture basically, right, into T average, or I can say it is T average. The molecular weight of mixture is equal to molecular weight of M, I am writing, is nothing but here 1 over Y I by M W I, right. I can write down that as 1 over 0.275 by 16 plus 0.11 divided by 32 plus rest will be I will be taking as nitrogen 0.8625 by 28 is equal to 27.81. And if I will do that, that is basically pressure, if you look at is given 101.325 pascals, this is the ambient pressure is given, right, and is equal to 8314 divided by 27.81 into average temperature is 1724.5 is equal to basically coming as 0.1965 kg per meter cube. So, if you look at, I know all the values, I know y average here, this molecular weight average, I can evaluate that. This is basically equation 3. Substituting the values in equation 3, we can get as get is equal to 1.16 into 1.04 into 10 power 11 exponential 15,000 1724.5. Average is 965 power to 2.2 into 0.0275 by 16.11 by 30. Right, is equal to 36.21 kg per meter cube per second, and alpha we can evaluate alpha as kg at T average by rho u 298 Kelvin, CPT average is equal to 14.7 10 power to minus 3, 1.18 into 1271.5 is equal to 7.64 into 10 power to minus 5 per second. And now in we will substitute all the values in the equation 2, right. In equation 2 we will get SL is equal to 32 by 9 into this is 7.64 10 power to minus 5, density is 1.18, and nu will be happen to calculate as a 17. This I have not done, but you can calculate that 17.16 plus 1 into 36.21, it will coming around something 0.389 meter per second equal to 38.9 centimeter per second. So, if you look at the approximate values, or if you conduct experiment, it comes around experiment something around 40 centimeter per second for methane air laminar flame at phi is equal to 1. There is something you can say it is coming roughly, but however, a lot of assumptions are being taken, and then some average properties are taken, and this is not very exact, but it will give you some ballpark numbers which will be helpful to understand, and it encompasses all the features, like it is a function of equivalence ratio, and then inlet temperature and pressure, and also the inert addition. So, that is giving the flavor of all the things. It is a very simple analysis, lot of assumptions we have made, and we can utilize that for our calculation. However, for the real situation you need to invoke the multi-step chemistry and then compute all the thing which can be done by numerically, right, or asymptotic analysis. And again asymptotic analysis is an approximation where single step chemistry will be using, right, will be used, and there the activation energy should be very high, then you do some kind of a approximation there. And with this I will stop over here. In the next lecture we will be discussing about how to relate this burning velocity to various other parameters. That we will be doing in the next lecture.